Here's the Spark code that we're going to use to start looking at this. We've got a collection of to-do points in this text file called 5000points.txt. And when we do the hands-on exercises, these files actually are available in the big data package we're going to copy over. So if you wanted to play with this yourself, you could. But for right now, we're just going to talk about how it works. So we count how many records there are. There's 5,000, as we expect. And we take a few and we see what format they're in. There's a bunch of white space. There's a couple of numbers and a bunch of strings. So we're going to have to do some things to clean this data up first. So the first thing we do is we run a split command with a map function, which is going to take all of these and convert them into tuples or pairs that have each of them the two integers, and it gets rid of the white space. And please take note of this split function, because that's going to be very useful in the hands-on portion if you want to do the exercises for PySpark. So we end up with this. We've got these coordinates, each in a tuple. And then we run a map function that is going to we've got it into a pair RDD form now, and we're ready to proceed, right? So we're going to use the k-means algorithm to identify clusters in this data set. We read the RDD, we transform it into pair RDDs, and now we import the k-means library. And here's the documentation for the k-means function. And it takes an RDD and a number of clusters as mandatory arguments. Then there's a bunch of other arguments that you can give it. One of the things that's worth mentioning is the seed argument. So if you want reproducibility, you can provide an optional seed, but by default it will be a random seed, which is very common in this kind of processing, and ultimately allows you sometimes to break out of some log jams and to just allow you to proceed, basically. So how many clusters do we ask for? Because we do have to tell it how many clusters we have, and you might be thinking, well, hey, isn't this supposed to be doing the clustering for me? And that's not exactly the way that it works. So let's see. Here's the code that we use to generate between 1 and 30 clusters. So we start out by suggesting if we do 1 cluster, and then these are the distances from the center points that it creates to guess where the clusters are. Okay. And these distances are they're quite high at the start, and then we get to an optimal one around 15. And I'm going to show you a chart of how these rule out, since the symbol notation doesn't make it very easy to read what these outputs are. I'm going to go to this real quickly, and then I'm going to show you a demonstration of how the k-means algorithm works, because I think that's really interesting. So with this, this graph is going to show you that the error or loss, which is the distance between our center points and where the items throughout, is very high if we start with a very low number of clusters. And that kind of makes sense with that scattered picture. We know that there's a lot more than 1 cluster, a lot more than 2 and 3. And as we sneak down here, we get down to about 15, and it starts to sort of bottom out. And you might think, well, why can't we just go with 30 clusters? Why don't we just take as many as we can? And the answer to that is that at a certain point, you get what we call overfitting. And you can think of it as, well, we've got 1 point for each cluster, which doesn't actually tell us anything. It doesn't tell us how anything is grouped. So it kind of defeats the entire purpose of the exercise. And we're going to find that that continues to be a problem long after we're able to look at the results in a simple 2D graph. We get to this point and we say, well, that's a pretty good guess. So we're going to make some other attempts at working with that. But before we move on, I want to talk about the k-means algorithm and exactly how it works. So this is a demonstration I found on the web that I found that is really useful. It was from a blog from Naftali Harris, and it's going to let us do our own experiment and see the process of the k-means algorithm as it goes. So let's see here. Can I share this? Okay, so someone want to shout out how many clusters you think you see here? Someone shout out a number. 7, wide agreement, we think it's 7? Okay, yeah, I think that's reasonable. And we could do that pretty quickly. That's easy for us to do when we're looking at a picture like this. We do it intuitively. So what I did is I created a bunch of packed circles of dots here. And the way the k-means algorithm works, it's going to add some randomly located dots, and we're going to put 1 for each cluster we think we have. And this demonstration is shading in the regions, and what they represent is all the points that are closer to that centroid of that color than any other. So the ones in the purple there that are near the border, they're closer to the purple than the blue at the top, and the ones at the blue are close, inside the blue are closer to the blue one. Now, what we're going to do, though, is we're going to have this iterative process where we go, and we're going to shade them all in, okay? Now, we're going to move those centroids from where they started in their random spots to the center of all of the groupings of dots that are closest to them. So we're going to rearrange the centroids, and then we're going to sort of wash, rinse, repeat, and see what happens. And sometimes this doesn't work. We might get stuck with some centroids that don't make a lot of sense to us, but it usually works. So let's see. Okay. So now you see in the red, there's some that are green because they used to be in the green region, but now they're closer to the new place for the red centroid, et cetera. Okay, so we recolor, and then we update. Color and update. We're already getting closer to what our intuitive sense of where these is, I think. I'm going to go a little faster now. Come on, come on. Oh, red and blue, are you going to do the right thing? Oh, look at that. And eventually we're going to get to a point where it's stable, and when we recolor, nothing happens. We don't have anything else to do. So that's when k-means decides it's done. And I think this matches up pretty well to our intuition about where those clusters are, right? So this is what k-means is doing under the hood. Okay. Yes? Well, yeah. I'm pretty sure there's a way in the k-means for PySpark, and even in this demonstration. Let me see if I can go back to it here. Oops, I lost it. Okay. Well, the answer is yes. I don't want to dwell on this for too long, but yes, I'm pretty certain that you can identify where you want those to start. However, starting with random points is it tends to work pretty well, and often, if you have a hint, then you could use it. But often, the kinds of problems you're going to be applying this to are ones where you don't really have all that much prior information, I think. Okay, so what is the exact answer here? We're going to look at some refinements on this procedure, trying to find exactly how many clusters we've got. There also, incidentally, are helper algorithms, the Python k-need package, or alternative metrics like the silhouette coefficient that can help you to decide how many clusters you might start with, but those aren't necessarily necessary. So, okay. So, in order to do this, we're going to start looking at the clusters in the range of 12 to 18 because we decided that somewhere around 15 is probably the right one. And here's some of the outputs that we get. And sometimes it looks like we get the best fit with 16, sometimes with 17, and then sometimes still with 15. So we're in the right ballpark. Then we're going to narrow it down here. We're going to try 10 times to find the best result. And we're going to get a couple of different results at 15, and we're going to actually map them out with matplotlib and see how we did compared to the actual image. So this is the plot from our from that 5,000 points file, and let's see how our 15 points match up. Again, it fits pretty well to what I think our intuition of where those clusters are going to be is. But it did pretty well at 16. How do we do with 16? Well, maybe there's actually an extra cluster on the bottom there, maybe not. Go back, we can see how it looked with 15, and then we can see with 16. It's, either one is reasonable. Still gives you some insight into your data, but 15 probably, I think, fits our intuition best. But we're not necessarily going to have that kind of information when we're dealing with very high dimensional data, and that's one of the points we're going to have here, is that this gives you a way to feel around where you can't actually see when you start to work with very high dimensional data. Just a brief word about how useful this data can be. A lot of physics and astronomy work, just for example, needs to detect and distinguish these sorts of signals, and tools like this can help find these solutions. And it doesn't have to be PySpark or even the k-means algorithm specifically, but we thought this was a good starting point for helping you to figure out how, with your own investigations, you'll be able to make sense of very large collections of data. And this is the end of the first slide deck here. I'm going to go a little bit into the machine learning and deep learning stuff because we have more time than I expected I would at the end of this. But I just wanted to leave you with a few insights about what it is that we're doing here before we get into the exercises, et cetera. So the data is naturally messy, and it extends into higher dimensions than we can easily visualize. It's nice when we have a 2D picture of it. It's very easy to intuitively interpret that. But reducing dimensionality and bringing it down to a level where we can see a picture that sort of represents that is the key to conquering these problems. Doing so provides us with insights that maybe we wouldn't have expected. And that is because learning is, in a very real way, finding a compressed representation of data. Learning is compression, and you're trying to find shorthand, you're trying to find rules, you're trying to find ways of interpreting multidimensional data and reducing it and boiling it down to smaller bits of information. It's creating a useful abstraction from real, dirty, messy data. So we're going to look at some more interesting ways of doing that. So let me switch up the slides here for a second. Here we go. So let's consider a case like this where we have a very high dimensionality collection of information. This is like from a store, like maybe from Amazon or something like that. It's a collection of purchases with 2,900 categories. If we're going to categorize that, we start with one dimension per item. And that is going to be very hard to do any clustering with, to do any graphing with, just as it is. So we're going to have to find a way to make it into something that's a little bit more manageable, because 2,900 dimensions is a lot. So when we do some clustering, we find that some categories will let us significantly reduce the dimensions down to 80. Okay, and so we've compressed this data, and we learned something about our customers, and that in itself can be a useful insight. So we've got these clusters of maybe young parents who are buying, baby monitors, and also maybe they, are buying new minivans because they need more space, or college athletes, who are buying a lot of protein bars. I don't know, auto enthusiasts, knitters. You can certainly imagine what these people might be buying and how they fit into groups. But you also might find some groups that don't necessarily line up to what you expected. And again, that's where the insights come in. You might find clusters, ways of reducing the dimensions into ways that create groupings that in ways that don't align with your intuitions. And so, we can use this kind of information, like we can figure out who we want to send a dashcam promo to, or what we want to do with that kind of data. So we've got ourselves down to an 80-dimensional vector. And this is a good time to point out how our intuition can lead us astray. So in higher dimensions, there's more pathways for randomly distributed points to be close to each other. Okay, there's more pathways for randomly distributed points to be close to each other, but also more directions for pairs of points to miss each other entirely and to sort of, or vectors to never intersect. So this is called the curse of dimensionality. And these plots will show you the pairwise distances between randomly distributed points within different dimensioned units of hypercubes. So we start out with this one where we've got very low dimensionality and we've got a nice distribution. These are randomly distributed points on a 2D frame, right? And it's a nice little bell curve. And we go up to more dimensions, and we get a little bit more of a spike, and a little bit more, and a little bit more, until in the end, almost everything is the same distance from everything else as you go up in dimensions. And this means that some of the algorithms don't generalize well from the 2D world to the 3D and the 4D and the 5D and many more dimensions. So we're going to have to think about the right way to get that information and the right way to reduce our dimensionality down so that we can break it into the kind of pieces we can actually work with. So even the definition of distance can vary based on the application. So if you're solving chess problems, for instance, you might find the Manhattan or taxicab metric to be the most useful. So you look at this, and it's not hard to see that the Pythagorean theorem will give you the length of this green line, but the blue line is actually equivalent to the two red lines together, just because you have to do just as much vertical and just as much horizontal work. So you care very much about how your data is structured and what the meaning of your data is. So that's going to make a big difference in how you interpret what comes out of it. For comparing text strings, for instance, we might choose one of a dozen different metrics. Spell checking might want to know about phonetic distance, or maybe edit distance. Natural language processing, you probably care more about tokens. genomics, you might care more about string sequences, and some useful measures don't even qualify, usually because they fall for the triangle inequality. So Spark k-means has a set distance measure, but I've seen no examples of its use also. It's just one mention that it could be used for cosine distance, so that's something to investigate if it's of interest to you. But anyway, so let's consider an alternate method for dimension reduction, principal component analysis. So this is a common way of doing it with linear data, and it works pretty well. Whoops. So we've got this 3D data set, and we can draw a line pretty well through it that gives us a nice trend, and we can see pretty well that it fits nicely. Here we've got a little bit more flat 2D data set, and it's not necessarily going to work well. So why so many alternatives? How we find the clusters in this data? Let's say we're trying to do a Zillow type of analysis and predict home values based on multiple factors. So maybe we're going to guess that there'll be some clusters like around the airport or noisy places. We might find that we don't necessarily we find lower values, for instance, or we might find that the width and depth of the lot has a lot to do with the ultimate value of a home. We can hypothesize about these things, and then we can test them, and we can see what actually happens. So in this case, we've got house price in a 3D grid here against both the width and depth of the lot, right? And it doesn't actually line up all that well. And that seems like a surprise. You'd think the bigger the lot, the higher the price would be. And it kind of does, but it doesn't line up perfectly. But if you take the depth times the width, the actual square footage, then all of a sudden you get a much better fit. And that's a hint that sometimes our relationships between the clusters or the bits of data that we have might not be linear, right? So maybe there's a better approach to this. So a lot of effort has been put into finding and reducing the dimensions of data in linear ways, in finding linear relationships. And it reminds me a little bit of the old joke. There's a cop who finds a man, he's looking around on the ground under a street lamp, and the cop asks him what he's looking for, and he says, "Oh, I'm looking for my car keys." And he says, "Okay, I'll help you." So after about 10 minutes, the cop says, "Well, are you sure you lost them here?" And the guy says, "No, I lost them over there, but the light is so much better over here." So when we try to find relationships in our data and we expect it to be neat and pat, we're going to be often disappointed because we find that the real world just doesn't work that way, and that we have to find more complicated relationships in a lot of times. A lot of the work in setting up neural networks is really aimed at that. So we're going to talk about an example that works with the MNIST data set to do character recognition. So I remember very well some of the early attempts at scanning and doing character recognition that were just absolutely abysmal. And these days we're getting pretty darn good at it. So this is a collection of grayscale images that have RGB information of 28 by 28 or 784 pixels, and we treat them each as one dimension of the problem, right? So here we've got a 9, and if I press a button, 1 pixel changes. I'm not sure you're even going to see it, but in the bottom left, you'll see that one of them gets darker. There it is. Okay, it goes from 258 to 93, and they look very much the same, but they're actually not exactly the same. But it's 1 dimension off, 1 dimension different. So, if we're looking for clustering, we'd say these are really close to each other. They're probably the same number, right? Intuitively, we can say that, but how do we convince a computer that that is true? So here's another example, a 2. So we need to find a way to reduce the dimensionality of these manifolds, and some of them are going to be a lot more complex than a 2 on a two-dimensional grid. So, for instance, in order to work with them, these ones I think look kind of like flowers. I'm going to refer back to them during the discussion of deep learning later. These are 3D, of course, but our problem has 784 dimensions in this case. And the point remains that data can be expressed in less dimensions, and we really have to get good at understanding and manipulating these higher dimensional things to reduce them down and be able to sort of chew them up. So I'm not going to spend a lot of time here, but this is scikit-learn code that can be used in order to use the linear PCA algorithm to do some clustering and reduce this matrix from 64-dimensional down to a 2-dimensional image. And it works reasonably well on what turns out to be pretty linear, pretty linear relationships, and doesn't necessarily work so well when you start working with higher dimensional things. So let's take stock. So we're moving from our big data processing to classic machine learning methods, and our tasks are moving very quickly into modern neural nets and deep learning. So I seem to be way ahead of time, and I'm pretty close to starting the deep learning material. So I'm going to pause here and take stock and see if there's any questions before we just dive into the stuff that I planned to do this afternoon, and then we'll have more time for exercises. So any questions or discussion? Okay. So deep learning, and there is a hands-on exercise for this, which I'm going to describe, but obviously we will defer until this afternoon before diving full force into that. So we're going to talk about the practical application of modern deep learning techniques, and we have some time this afternoon to work on the exercises. I know, again, some of you already live and breathe this stuff. My goal is just to get everyone up to a functional working knowledge of deep learning and computation, and in particular the way that we can use TensorFlow to do it on Bridges 2. So the exercises are deliberately open-ended and really just represent a starting point for you to anchor your understanding so that you can explore the particular topics that are of interest to you. And again, let me remind you that if you want to continue using Bridges 2, your account after the school will remain active for some time, and it is trivially easy to obtain a startup grant anytime you want to continue using those resources indefinitely. So if you can look at our at the psc.edu website, or talk to me if you need any help in finding out how to make that happen. So machine learning in the sciences went from who cares 10 years ago to whoa, this works way better than anything else today. And meanwhile, all the knowledge is usually still walled off in the computer science community, and usually takes semesters to learn it. It's a huge knowledge gap for practicing scientists, so here we are. Neural nets have been around for quite some time, but only now is our computational power really catching up with our ability to make these algorithms do useful work. And 10 years ago, this all still kind of seemed like science fiction. Now we're finding that maybe these methods are becoming superhuman in a number of fields, and it's coming back to science fiction in another way. So, we had neural nets will enable real-time ray tracing. Sure, okay. Neural nets will do protein folding. What is that? And then 5 years ago, well, maybe we'll do CFD sometime soon. And then today, neural net and algorithms are the best way to do protein folding. And tomorrow, maybe Skynet kills us all and steals our jobs. I don't know. So why now? GPUs and big data together have created a field that's moving incredibly fast. The ability of GPUs to do matrix calculations incredibly quickly, it just happens to line up perfectly with the methods that are used to train neural networks. I remember being asked about this, before I actually started doing the big data training, but by some students about using GPUs to do sort of this specialized computing. And at the time, I compared it to all the other special purpose processors I had heard about over the years. And usually what happened was they took a great deal of time to develop, and then by the time they were done, they were outclassed by general purpose processors at the job they were designed for in the first place. So I was skeptical. But I don't think there's any denying that now we've come to the point where GPUs are radically changing the way that computation is happening. So, there's really, for a long time now, there's been no doubt about that. So there's two perspectives on the fundamentals of deep learning. One way of looking at it is that it's inspired by biological models that we're trying to model the way that synapses and neurons actually work. Another is to look at it as an evolution of classic machine learning techniques, like the perceptron, for instance. They're both fair and useful. We'll give each a slice of our attention and move on to the implementation. And you really, you can have your peanut butter in your chocolate and your chocolate in your peanut butter. You don't really have to think of it one particular way, but maybe it's easier for understanding if you take it in the way that you like. So. Brains have neurons. They're connected by synapses. And if we graph this, we have a matrix. And we find ourselves using the language of linear algebra to represent the way that biological brains work. Okay? And we've got here an image of a deep neural network, and then a relatively shallow neural network. And in this case, it's working on identifying some characters. And we've also got our image of the neurons up there, et cetera. So if we want to build a classifier as a pure machine learning program, and that's what we're going to be working on as our example here. For instance, let's say we want to differentiate between cats and dogs. There was a machine called the perceptron that was developed in 1943 as a theory, and then first built in hardware in 1957. And it was a linear classification system. It couldn't identify any complex or interrelated images, and so it was seen as a failure because it wasn't really very practical for any actual usage. Even though it could do some things which at the time were surprising for computers, but the fact that it was fooled so easily really was a deadly limitation. So many years passed. And now we come back and we're starting to think that, well, maybe these ideas, maybe we just didn't try hard enough in some sense. And now we can have these entangled data sets which require nonlinear techniques. We've discovered some ways that we can approach them with these hidden nonlinear layers that live between our initial perception, our sort of intuitive 2D perception of something like this, and that can change the image in such a way that we can do that differentiation and reason about it. At its core, the operation of a neural network is pretty simple. There's an input matrix, which is pushed into a hidden layer that performs a transformation on that object, which transforms and filters that input. And in my headcanon, this is like pachinko. Like you drop a token in, and it goes ba-dink, 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 and then it comes out one end or the other. Maybe that end is dog, maybe that end is cat, right? Of course, it's not just one token, it's an incredibly large number of tokens, and they all kind of, maybe it's more like those things where you put your cigarette butt in to vote for, who you want to be the president or whatever. In any case, this isn't actually much more complicated than it looks, but of course the hidden layer is where the magic is happening here, so we're going to get into what's going on in there to some extent. We're showing only one layer, but it can be arbitrarily deep. So we've got this picture of the deep neural network here. And the input can be simple or it can be complex. And the output could be, in this case, an entire image. It could possibly segment the image, restyle it. Again, we're going to work on an example that just tries to do some categorization of images. And we use hyperparameters as our way of determining how these neurons are going to process the pieces of the image that they look at are. And we can choose them to influence the operation of the entire network. The depth and the width can vary, and we'll see how those also can be manipulated in due course. So, let's see. This graph here represents a functioning trained neural network. We provide input, in this case, a picture of an adorable cat. And we provide input and expect to get useful output. Input could be pixel values from an image. Let's see. So here we have the weights provided in the input, and the connections between the neurons are weighted according to what they've learned in the training. This is inference, or if you will, the thinking step. So each neuron calculates something about the input and passes it along. And I'm going to get into exactly what training means and exactly how that works in a moment. So these weights are applied to the input as it goes through the network, and each neuron passing information to all the neurons in the next layer. Each layer performs its own calculation, or we'll call it an activation. We're activating the neuron and saying, hey, neuron, chew on this piece of information for a moment and tell me what you think. And based on the preceding inputs, it takes that input and then passes it on to the next layer and so on until our pachinko comes out the end, and we have some probability of cat, some probability of dog. And in this case, we've got the weights changing. So let's talk about what the activation functions mean. This is what is sort of the magic that happens at each neuron, each little step inside of your neural network. The transformations are being performed inside the hidden layer that typically depend on nonlinear activation functions. So early attempts would try to use a function like the sigmoid function there, that nice S curved scale. But experiments show that a rectified linear function can be a lot more efficient. It's 0 when it's negative. It's linear, equal to the input. That's that bottom picture there, if it's not clear. It's equal to the input when it's positive, which makes the calculation very, very simple, and the derivative will always be the same there. And it handles sparse activation between a little bit better by filtering out garbage. So for classification systems in particular, the rectified linear, or as it's referred to in practice, the ReLU activation format is very effective in kind of getting rid of or filtering out the garbage and just ripping the Band-Aid and making a decisive choice. It's easier computation and mostly just a simple comparison. So there's lots of variance for the kind of activation functions that a neuron can have, but for classification, activation, the rectified linear is the one that is generally considered to be the most popular. So here, we're going to see the application of these weights using the sigmoid function. Each neuron operates on a piece of the data, and the end result is a calculated weight, i.e. where the pachinko fell. Okay, so our output 1, in this case, it's 0.35 chance of cat and 0.85 chance of dog. Okay, and we've got the output values from our simple network there. And these operations lend themselves nicely to being performed, again, on large matrices, which makes them perfect for GPUs. We've got vector matrix multiplication here. It's all simple linear algebra, and our output is just another vector for the next layer. So when all you have is a hammer, everything sometimes looks like a nail, and this happens to be an extremely useful nail. So let's talk very briefly about biases. This is one of the hyperparameters that you can adjust. They introduce a constant that allows us to adjust our data and perhaps to constrain the output or to center the activation function. So we're going to come back to this picture of this graph, and this is very important. So you might remember we had all of those conjoined S curves, or the shapes that you couldn't draw a line through. So if you want to have a categorization system, you have to draw a line between them and say everything on this side is one thing, everything on this side is the other. So we can use our matrix multiplication to provide skew, rotation, and scale on the graph that represents our data. Okay, and that means we can make things bigger and smaller. We can turn them. We can rotate them. The bias is going to provide the translation. In other words, often that's going to give us sort of a rough starting point, or convert the output into a useful format. But the activation function does that warping process. So that's what's changing the actual shape of the graph that we're working on, and that's going to turn out to be the key to being able to differentiate these interrelated bits of data. So let's take a look here. We've got a demonstration where we're finding these entangled data sets where you cannot draw a line between them at the start. The network is learning to separate them. The left side is succeeding quite nicely, actually. You could draw a clear line between them. The right side is not. And sometimes bad hyperparameters or sometimes even just unlucky seeding can leave you with that result. So we do lots of experiments in order to try to find the best options, and sometimes we just don't get there. But this process can be duplicated on higher dimensions. So let's consider this picture. So in 2 dimensions, no amount of twisting and warping can draw a straight line between these two because the bullseye is completely surrounded. But adding a 3rd dimension will allow us to draw a plane between the red part and the blue part. Okay? So we can twist and warp and add a dimension, and all of a sudden, this is comprehensible as a way of distinguishing. So in 3D, we can succeed where we did not in 2D. However, 3D might not be enough. Here we've got these 2 donuts linked together, or chain links, or whatever we want to think of them. I think I'm hungry because I see donuts. But for this, we'd have to go to 4 dimensions, and it's not something I can visualize for you, but with a hypercube at 4 dimensions, you can, in fact, draw a line between them, and you can keep doing that. And, it gets more complicated, but it is something that a neural network can learn from in a way that we start to have difficulty really understanding ourselves, and that's where some of the really surprising results in neural networking actually come. So, let's talk for a moment about the theory behind this. There's a universal approximation theorem that a one hidden layer feed-forward network of this type can approximate any function given enough width. If you think about what that means for a second, it's kind of a dumb thing to say, I think, because you're kind of trying to say, yes, you could have a lookup table that will hand you every result given a certain specific input. But in practical problems, of course, we don't have the ability. It's impossible to consider every possible option of, certainly of any problem and of any meaningful problem. So we still don't know how to find these weights in the first place. So let's talk about if we're going to have a deeper network that is going to be finding interrelationships, since we can't just have a single layer of a network finding our answers. We have to figure out how we can adjust the weights to get useful information out of them. And that's going to be a lot of the work that is going to be done in deep learning, and specifically in the examples that we're going to consider in our hands-on work. So training neural networks. So when we train the neural network, we give it a bunch of data that we know the answer to, right? We say, here are, in our case, we're going to give it a bunch of images, and we're going to give it, this is one thing, this is another thing, this is the category that each one falls into. And it's going to guess what they are, and it's going to see whether it was right or not. And then, if it's not right, it's going to go back and make some changes, and we call this backpropagation. And in my head, again, I have a little bit of a headcanon for this, and it's like a game of Marco Polo. Do you all play Marco Polo in the pool? One person yells out, Marco, and the other person yells out, Polo, and one person has to keep their eyes closed, and they have to keep getting closer and closer to where they're hearing the sound. And I like to think about backpropagation like that. So we look at the outputs, we look back at the neurons, and we decide what to change with the weights of each one that would bring us closer to the truth for any given input. We're going to see a visualization of this process which later on, which I think makes it really clear. But here's a short look at backpropagation. So here we have a more complicated network, and in the process of trying to reduce our error, we backpropagate. It would be too costly to evaluate every value for every node. Again, it would be like trying to do that one layer node, and we certainly can't do that. So instead, what we do is we identify erroneous output, and we work backwards to the neuron that's most directly responsible. And this is done through the application of the chain rule from calculus. I'm not really going to go into detail of the math. It's there for you. There's a million explainers on the web, and you're going to find a lot of people who will explain it, frankly, better than I could. But the idea behind it, oh, well, the other thing that's really important to know about this is you really don't need to know. You really need to know what it does in principle. You need to know how it works in order to get useful work out of this. So anyway, since the output is a chain, the result of a chain of weights, we can craft an equation that identifies how much to push a particular weight somewhere in the network in order to bring the error back under the level that we configured. It's simple to do for a single layer, but when you want to apply it to the weights farther back, you want to see what the change would be with respect to a particular input. In other words, by applying the chain rule, by holding the input constant and taking the derivative at each layer. In this way, each training input lets us adjust each neuron in a way that gets error within acceptable parameters without forgetting anything, rather just emphasizing the influence of good pathways and de-emphasizing the ones that are bad with precision. Again, I think it's like that game of Marco Polo. So here are some resources if you are interested in learning more of the specific math that are very good. It's a full deep dive into backpropagation that is, again, beyond our scope, but go ahead and check them out in your time. So let's talk about solvers. So in practice, we quickly find that we again have a dauntingly large collection of equations to solve, and the solution space might have an ugly non-convex shape like this graph here. We use a system called gradient descent to find the minimum or the least error in all of this. The error is the degree to which we're getting the wrong answer, and that is what we want to minimize. So we're looking for the minima within these systems. It's a standard method to quickly find minima in a complex landscape, and the minimum represents the best collection of weights, but how do we get there? We could try every single spot, but again, we want to avoid that. That doesn't work. That's going to be prohibitively costly on any real data set that we care about. We can be more efficient by taking what we call a stochastic or statistical approach, where maybe we go through a sample of the data and make a best effort and iterate through those batches. Gradient descent, regular gradient descent is kind of like a person who is taking very careful steps all the way down a hill and counting them so they know at the end exactly how many they had, whereas maybe stochastic gradient descent is like a drunk who's quickly staggering their way down there, and they're going to get to the end a lot faster, maybe not with as much precision, but they'll get there. So this is for the practical application of it. For the hands-on work, I'm going to go through a little bit of how this works, and I'm going to return some of our time to us here. But when we do this, we're going to work on some examples, and we're going to look at how this works with our MNIST character recognition, and then we're also going to do an exercise with another data set. So one other note here is that the TensorFlow API documentation is surprisingly good. Don't be shy about digging in there. And one final note, which I'll repeat when it's time for the hands-on exercises, is that in addition to the slides on the Moodle, I also included a commands.txt file that has the commands you need to get yourself set up to connect to bridges both for the PySpark and then separately for the GPU. You're going to need to connect differently for the two different problem sets, and we'll deal with that when it's time. But okay, so let's talk about this MNIST data set. So we'll take this collection of hand-drawn numbers and attempt to set up character recognition, learning to read handwritten digits by training on a large collection of those images. And then we test our network against a testing data set, and we see how we did. So the classic example, it's a classic example rather, with manageable training times, and helps to illustrate the principles that apply equally well to more intensive data sets. And all the grayscale images are included in TensorFlow. So when you leave here, if you download it onto your laptop or whatever you do later, you'll be able to do the same work. So using TensorFlow in these exercises, there's other software out there like PyTorch, and Keras used to be a separate piece of software. They were originally considered sort of user-friendly, but a little bit less production-ready. And then eventually Keras was rolled into TensorFlow, and it's a whole history, and it's a thing. But we're going to use Keras with TensorFlow today because Keras is a very friendly front end, and TensorFlow is a very effective back end, and it's very well documented. So that's where we're going to go. Nothing wrong with PyTorch, no knock on it. Data set in this case also includes labeled images of numbers, and it's got test images broken out to ensure that we don't overfit. So those will not show up in the training set. And those are the ones that we use afterwards, after we've done our training, in order to see how we did and see just how effective our neural network is at doing this character recognition. There's matplotlib code here that's just to demonstrate that the numbers in our data really are these grayscale images, to convince ourselves of it. You probably can't run this on Bridges 2 again without setting up exporting, but it is possible, and if you're doing it at home, more power to you. So our images are 28 by 28, but in this case, our simple network is going to take 1D linear input. So we're going to stretch this one out that way, and that means, again, 784 dimensions, 784 input neurons. And that's going to be a fixed value just based on our input. So that first input layer is always going to have that. Now here is where we get to define and initialize our neurons. Dense, the function dense within TensorFlow is going to create a densely connected neural network layer. And you can just think of it as this is a standard neural network layer, but it's called dense. The hyperparameters we're going to use, we're going to start with 64 neurons in each layer. And you might ask, why 64? Well, you could try more, you could try less, and you can see how it affects speed and accuracy. We're just going to start with 64 because we need to start somewhere. So that's where we'll start. The input side, of course, has to have 784 entries because that's how we stretched our image out. And the output is constrained to be 10-digit categories because those are the number of categories we have. So to get useful information, that is constrained as well. But the other hyperparameters are up for grabs. So the first two, let's see, do I have to click here again? Yes, there we go. The first two layers are going to be activated by rectified linear functions, or ReLU again. And then softmax is going to convert to probabilistic weights from 0 to 1 for the output. So it just normalizes our output. That's effectively all that that does. We're going to need random numbers to initialize the neurons, but fortunately Keras gives us usable defaults. We'll defer to that for now. And again, if you want reproducibility, or if you want to have some sort of hinting, then you can set different seeds, but that's, the defaults are sufficient for us for today. And let's see, model.summary. Let's see, here we go, is going to provide some introspection here so that we can see even a pretty small network quickly rises to over 50,000 trainable parameters. And you can imagine these get really massive on much larger data sets. So we normalize this output using softmax, and here we go. We've got probabilities that add up to 1. We've got the values coming out of our output. We apply an exponential function to them, and then softmax is going to get rid of the negative values and convert all of the others into percentage that will add up to 1. So 0.87, we're pretty sure our digit in this case is 0. There's a small chance it's a 2, and basically no chance that it's a 1.